Hi, I'm Antonio Sala, and in this video we are going to continue with our discussion on the intuitive interpretation of the singular value decomposition and the principal maneuvers associated to it, the SVD of the DC gain. The overall goal is understanding that SVD can help me decide that a good option could be fusing sensors by controlling some weighted sensor averages, and we can also fuse actuators, operating them in a coordinated way, and the singular value decomposition would tell me a way to share the load. Well, so the objective of this video is understanding that intuition on plants with one controlled variable, for instance this one in which I have a heater in red, a resistor let's say, and a blower blowing cold air in green, and I just have one temperature as controlled variable. Of course, common sense can dictate us what to do here, we'll discuss it later, but our goal is relating that common sense ideas with the singular value decomposition. Let us start by reviewing the basic theoretical ideas from the previous video before delving on the particular case. If we had the DC gain of my process, I could carry out singular value decomposition of it. The columns of U were the output directions of the principal maneuvers, the columns of V were the input directions of the principal maneuvers, and the diagonal of S contained the gain of such principal maneuvers. The pseudo-inverse of a matrix is associated to the singular value decomposition by swapping U and V and inverting the non-zero elements of the diagonal of S, so principal maneuvers are close cousins to least squares problem solving. And we also discussed that making this change of variable, the thing is that we could express the DC gain between Y SVD and the U SVD as the diagonal matrix S. Just note that we have a capital U denoting the matrix of the singular value decomposition and the lowercase u denoting my control action. Try to not get confused with when I say U, depending on the context, it will be the SVD matrix or the controller output. The thing is that we have this diagonal behavior between these two virtual, let's say, input and outputs. So, putting all change of variables together, we get this SVD controller, or if we decide to control a reduced number of principal maneuvers to avoid bad conditioning and high likelihood of saturation, we do that with a piece of the capital U and capital V matrices, and this formula plus some scalings end up in this block diagram. This is the review of previous materials. Let us now concentrate on what the SVD interpretation would be for this system. We will work in, of course, linearized modules, because the DC gain is the DC gain of the linearized system. Then our controller will decide the increment of U1 with respect to the U operating point, and likewise, we must decide upon the increment of U2 to be added to the U2 operating point. We will assume that we have an operating point, say around 50% of the operating range of these actuators, and that we will make some scalings so the allowed increments in scaled units will be plus minus 1. Of course, if we have a highly asymmetric interval of feasible increments, then this analysis may not be accurate. But okay, linearization assumes symmetric behavior up and down, then we'll stick to that. So which will be the DC gain of this resistor plus blower temperature control system? Well, we may have a DC gain in whatever physical units but after some scaling, say the blower can increment or decrement its power in, let's say, 0.2 units, whatever they are in physical terms. Well, the thing is that the scaled gain is just a rho 1 minus 2. That means that fan at full power, maximum increment till saturation, is able to have double the cooling effect than resistor at full power, maximum increment to saturation. Of course, this is a pure invention. I mean, 1 and 2 are just invented to get a clear intuition. Well, we have this G scaled. Then let us do the singular value decomposition. Here we have it. As we have just one output, then output direction is just scalar 1, so there is no capital U matrix. And then the principal maneuver is moving my actuators in this direction, and that principal maneuver has a gain of 2.23. This thing is the null space we'll comment upon in a minute. Let's first understand what this 2.23 means. Well, in fact, as this G scaled is 1 minus 2, the thing is that the singular value decomposition of a row vector or a column vector has the norm of that vector as the singular value, and in this case 2.236 is square root of 5. And in fact, the principal maneuver is just dividing the vector by its norm. So it is the unit vector in the direction of 1 minus 2. As you can see, if I multiply 0.447 times 2, then I get 0.894. Well, of course, negative sign to keep the minus 2. So if the transfer function matrix is a row vector, SVD principal maneuvers are just computing the unit vector in the direction given by that G scaled, and the norm is the singular value. That is a maneuver with maximum effect on the output. And if we now concentrate on the null space, which is this maneuver means hitting 2 units, the resistor, and incrementing 1 unit, the heater. Proportion is also 2 to 1, but it's in the perpendicular direction. So this thing is perpendicular to 1 minus 2. It's parallel to plus 2 plus 1 orthogonal vectors. And what does it mean in intuitive terms? Well, if I increase 2 units the resistor and I increase 1 unit the blower output, then the extra heating is exactly compensated by the extra cooling from the blower, because its cooling effect is twice as powerful. So regarding temperature, we would do nothing, but we will increment our actuator power doing nothing. So that null space maneuver is somehow useless and nonsense if I wish the smaller input increments in the least square sense, in the sense that incrementing my inputs in this direction would produce input increment with zero effect. So least squares, the minimum input increments achieving a given temperature would be related to this principal maneuver and not to the null space. I mean, least squares ends up summarized in just avoid the null space. Indeed, if we compute the pseudo inverse of my G scaled, well, here we have it, and pseudo inverse is 1 minus 2 divided by, instead of square root of 5 like V, square root of 5 squared divided by 5. But it's still pseudo inverse proportional to the principal maneuver, and it indicates that the control action achieving a lower increment U1 squared plus increment U2 squared, of course in scale units, is this one, in the sense that if I wish to achieve a given increment of temperature, I should apply this action, the pseudo-inverse, of course, and it is basically a load sharing proportional to the gain. The higher the gain, the higher the effort in scaled units I must devote in order to fit this least squares maneuver. In common sense terms, the best way to operate this when I wish to heat, let's say, is incrementing 1 unit the red resistors and decrementing 2 units the blower intensity. That would be the best way to operate in the least square sense, and the worst way would be incrementing 2 units the resistor and 1 unit the fan, because that would be the null space maneuver. It would have no effect. Of course, if I were controlling 2 things, let's say airflow for given ventilation needs, whatever needs to be another controlled variable, well, in that case, that maneuver would be associated to decoupling, in the sense that increasing airflow without increasing temperature would need that null space maneuver. So, null space maneuvers are to be avoided in temperature control, but are sought in, let's say, airflow control. But the thing is that if we understand the intuition here, we will be able to understand that intuition when we have a more complicated matrix full of numbers in the SVD, if we just remember this simplistic example. Of course, the pseudo-inverse computation related to the SVD is, the principal maneuver input direction, capital V, divided by S. That would be the inverse maneuver, and the principal maneuver is, capital V multiplied by S. So they are, close cousins, and the basic conclusion is indeed that temperature control only must be operated in the direction of this principal maneuver, increase 1 resistor, decrease 2 blower. So that idea can be thought as SVD decoupling block diagram, indeed. As capital U is 1, our change of variable is nothing, so we need no change of variable in the output directions. Then we multiply by the SVD decoupled controller. In this case, we have only 1 maneuver, so this KS will be diagonal of size 1, just 1 PID, and then this would be USVD, and with this we convert it to physical U. So in the end, we would send this temperature reading to a controller in which I would compare to a set point. I would obtain an error in SVD coordinates that, well, is just a plain loop error in this one output case. Then I will put some PID to carry out the temperature control, and its output, USVD, indeed it has transformed units because it's a virtual output that indicates how to share the load among the physical actuators, so that USVD would be multiplied by each of the coefficients in the principal maneuver input direction, 0.45 minus 0.89, and this would be the block diagram interpretation of this SVD decoupling. Well, I did not put scaling matrices because, changing units, multiplying by 5 or whatever is trivial. So this would be the interpretation of SVD decoupling in this very simple case we have used to try to give some intuition to the meaning of that input principal maneuver. But of course, this case is so simple that we sort of could have had the same intuition ourselves. And in fact, this would be a load balancing strategy. I mean, I am heating with the resistor and I am simultaneously blowing because maybe I have some chemicals and I need some minimum ventilation. in this process. But the thing is that maybe if I need no minimum ventilation, I could have decided that the operating point is, let's say, resistor at a given power and blower being off. So if my operating point of one of the actuators is at its extreme, then the common sense strategy would be the split range. My PID controller could be even an on-off controller, heating, cooling, split range, in the sense that, okay, if temperature set point is above my measurement, just switch resistor on. If temperature set point is below my measurement, switch resistor off and switch the blower on. Indeed, that would be a common sense, very simple strategy. So I am not saying that this SVD load balancing is the thing that I would put in this process. That depends on what I am trying to do and the airflow set point I wish to pursue. Maybe split range would be a good option, but the thing is that the goal of this video is not entering into the technological detail on what's the best thing to do for temperature control in a cooking oven. The goal of this video was getting an intuition and common sense interpretation on what this SVD decoupling means and what the input directions and the null space and whatever mean in this simple example. So if this has helped you get that intuition, then you will be better prepared to understand cases in which we have the singular value decomposition of a 6x9 matrix, let's say. So I hope I accomplished the goal. I finished the video here. Next videos will provide further examples. Thanks for watching.